So I'm Thierry Klein. I'm currently president of Bell Labs Solutions Research at Nokia Bell Labs. Bell Labs is the research arm of Nokia, and the focus of research is actually twofold for Bell Labs. One is research in the direction of the current portfolio of the company, new products, new solutions, new services in the direction of what the company is selling right now. The other part of research is to explore new technologies, new markets, new customers, new business models that would expand the portfolio of the company. And I'm leading the second part of the research organization. The mission of Bell Labs is really to solve hard technical problems to advance human possibilities and how we communicate, how we interact with each other, and how we interact more and more between us and machines and our environment, and what are the foundational challenges of our generation. That's been the challenge for Bell Labs through our almost 100-year history. What are the foundational problems of our generation, and then really solve those problems in a disruptive way. So we take, I'd say, a 10-year view, 5 to 10-year view, imagine the future, see what the technology challenges or the trends are where technology hits roadblocks, and then imagine what the future would be, and then work backwards from there. So we have a notion of future back. Imagine the future, solve the problems fundamentally, and then start building towards that vision of the future. And that's been I'd say the hallmark of Bell Labs as an industrial research lab over the last 100 years. The problems and technology domains change, but the mindset has been by and large the same. Well, I think we realize more and more as we're moving around, we need wireless communication. It's just operationally very difficult to have wires everywhere. So radio systems are important to connect us as people, more and more connect us to sensors, machines, devices. And so radio systems are really about freeing us from physical locations and allowing us to go anywhere and transmit information. It's a very difficult medium to transmit bits and bytes over air. So it's really all about connecting endpoints with each other and transmitting as much information as you possibly can. And so building the hardware, building the software, building the operational algorithms and software systems to allow you to transmit as much information between endpoints that can be anywhere while spending the least amount of resources. And resources mean the amount of RF spectrum you would use, the amount of power you would use, or the number of the size of the infrastructure you need to deploy to support that. Traditionally, we spend a lot of effort to do drive testing, measure the environment, optimize the network, figure out the configuration of the network, then deploy it, then test it. How do we reduce the burden to build, design, deploy, operate these networks and make it very, very easy, almost drop and forget, and the networks become very self-learning, self-configuring, self-optimizing, so that the time it takes to deploy the network, the level of expertise, and the time, the number of people that are required to deploy and operate the network is reduced, because that will democratize just the access to these networks greatly. And in a lot of environments, you don't want to send people into those environments because it's a very difficult environment to get to. It's a very harsh environment. So you want these networks to be very self-organizing, self-configuring. The lower the frequency, the longer your propagation, your range is, which is important for a lot of sensor deployments, for example. At the same time, when you want to deploy higher throughput applications, you need higher bandwidth, and that tends to go into the higher frequencies. So I think for us as a research organization, we're looking at all the bands, and quite frankly, our customers decide which bands they want to deploy. So we provide more the trade-offs and pros and cons of different bands versus we pick one. We understand the trade-offs, we understand the capabilities can be delivered in different bands, and we will build solutions and products for the different bands, but we don't have a favorite band. everybody that deploys infrastructure has access to certain sites, right? And you want to get your throughput up because you have more and more applications that consume a lot of throughput. So if you want to do more video, or you want to do AR, VR, and so forth, so your throughput demand and your traffic demand goes up. So you want to deploy new radio capabilities. You want to get into higher bands, but what nobody really wants to do is deploy a lot more sites, right? And so the trick will be, can you get higher throughput? Can you go to higher bands and still use the existing sites? That's why I think everybody's interested in this 7 to 8 gigahertz band right now, because the view is that maybe we can provide higher throughput and higher service while still being in the current sites that we have. Yeah, so we have a project right now to deploy a cellular network on the moon. It's a project with NASA. And the goal is really to show that you can take the same technologies that you and I use every day, that we have in our cell phones, that we take for granted every day as we communicate, that we can take those same technologies and deploy it on the moon. We cannot think of a harsher environment than going into space. So showing that I can take the same technologies that we develop and have, as an industry, having invested a lot of money over decades to build these systems, showing that I can take those technologies and deploy them in space and on the moon is one of the challenges. But of course, the moon is very different from Earth. There are lots of environmental and operational challenges. So you can't just take a cellular network that we deploy for a service provider on Earth, whether it's Verizon or AT&T or T-Mobile. You can't just take that same system and deploy it on the moon. But the core technology that's in that cellular network on Earth is the same. So how do we build purpose-built systems that have the right form factor, the right capacity, the right geographical coverage area, and are hardened for the environmental conditions? So that's the challenge. And ultimately, when we think about space, there's a great renewed interest in space exploration over the last 5-10 years, and all the missions that either government or commercial missions that go into space, go into the moon, go into Mars, they all require more and more communication capabilities, whether it's voice between astronauts, it's biometric information, health monitoring, or it's video, it's sensors, it's robotic assets. They all need more and more communication capabilities. So it's absolutely clear that we need advanced communication solutions to support future space exploration. And the question is, what's the best suited technologies, and how can we take all the lessons learned and the advances we've made on Earth, and how do we take those forward to the moon? Every country views leadership in 6G as being really fundamental, and that's 6G is very broad. It's the RF technologies, but it's also the networking technology, it's algorithmics, it's technologies, it's software, data, computer science, so forth. So 6G, you should think of very, very broad as the technologies that allow us to communicate and share information. You can't know everything about everything, but you have to have a broad understanding of a lot of different disciplines, but you need to be an expert in certain areas. So understand the fundamentals of that. More and more, it's going to be, as I said, about AI, computer science, software, data systems, certainly device technology, material science, device technology is very, very important. But I think ultimately, if you want to go into research, what you really need is not a technical bill. You need to be curious. You need to be curious. You need to be interested in problems. You need to see things that don't work, and then be interested in finding ways to solve those problems. And then you may not be the expert, but then you can find other people that you can work with. You bring your skills, your expertise, your areas of interest together with what others are good at. If you're not curious, if you're not interested in solving hard problems, very difficult to be in research. Certainly, what I learned during my PhD, we've moved on, right? That's old, like 5, 10, 15, 20 years later. It's the foundation that you get on how you solve problems that you learn. and then you apply those tools and those techniques and those methodologies, and the technology evolves. So you need to have your fundamentals, you need to have your way of solving problems, how you decompose problems, how you get to the core challenge of the problem that you're trying to solve. That stays with you.